Good afternoon, everyone. Welcome at the next session. I will be your company within the almost 2 upcoming hours. My name is Bara Kozlikova, and the topic of this session is biomedical image analysis. And we will be having 4 interesting talks here. And without any further delays, let's jump to the first one. And the first one will be presented by Faizan Siddiqui. And the topic is a progressive approach for uncertainty visualization in diffusion tensor imaging. So Faizan, stage or the video is yours right now, and afterwards we'll have a Q&A session together. So enjoy the talk.
Everyone, thank you for joining my talk. I am Faizan Siddiqui, and I'm going to present our work on a progressive approach for uncertainty visualization in artificial tensor imaging. Let me start with a brief introduction of our brain anatomy. A human brain consists of a gray matter and a white matter. Gray matter are the neurons, and the white matter are the connection of those neurons. The knowledge of this white matter structure is very important for a neurosurgeon, especially in a pre-operative planning and a post-operative prognosis. To get this information, the most feasible option is the virtual reconstruction of the brain white matter, as shown here on the right. This process is called diffusion MRI tractography. This method is the only non-invasive technique that visually represents the distribution of the white matter structure in a human brain. However, going from left to right is not a straightforward task. First, it involves the MRI stage, which has its own complication, and then the whole data has to go through the tractography pipeline. In our work, we are focusing on this tractography pipeline, which has certain sources of errors and sources of uncertainties. Tractography is actually a very powerful tool to be used in a neurosurgical workflow. It aids surgeons in various ways. For example, it provides the whole path of the white matter structure for the pre-operative planning and the post-operative prognosis. It also aids surgeons to define a safety path for the surgery. However, despite of these advantages, there are the different bottlenecks that limits the widespread use of the tractography in a clinical setting. One of the bottlenecks is the uncertainty involved in the whole processing pipeline. So here's the tractography pipeline. This pipeline involves multiple stages. Each has its own sources of errors, as can be seen here in the yellow box. These involved uncertainties propagates throughout the pipeline and adds undesired variation in the results. Due to these variations, there is no direct link between the data being acquired and being visualized. These uncertainties in the results limits the widespread use of the tractography in a clinical setting, despite of its advantages. Our solution provides a way to visualize these propagated uncertainties and inform the users that would help them in their decision-making process. To model the present uncertainties, there are 2 methods, analytical and stochastic. Analytical method relies on the direct solution. That's why it is always desirable. However, in a complex pipeline, where there are nonlinear operations involved as we have in our own pipeline, the analytical method of the propagation is not feasible. Due to this limitation, we use stochastic method in our workflow that are more feasible for our pipeline. It has certain pros and cons, which we will discuss later. Generally, in stochastic methods, we need hundreds of samples to model the uncertainties in the population. In our pipeline, to achieve this, one approach is to get the multiple acquisition of the same patients to get the possible variation of the fiber tracks, and then model the uncertainty. However, in a clinical setting, due to the clinical bottlenecks and the time constraints, it is not feasible. And also, the multiple acquisition can also lead to the additional sources of uncertainties, which can also lead to further complications. To circumvent this problem, we have used a simulation-based technique called mild bootstrapping. This technique has been introduced and widely used earlier in the literature. This technique relies on a single acquisition and generates the whole ensemble of the tensor volume. Once we have the adequate number of the samples, we can proceed with the fiber tracking and then the rendering. This pipeline provides the possible variation of the fiber ensemble. One limitation of this pipeline is that it involves the pre-processing stage that actually breaks the workflow. The pre-processing stage involved in this pipeline has certain limitations. One of that is that this stage is computationally very expensive. So our user has to wait for a long time for the pre-processing stage to end to continue with the other stages. The other limitation is that this stage requires a very large memory footprint. Since we are recalculating and storing the whole tensor volume ensemble, it requires a very large memory to store the data. The third limitation is that we don't know how much data we need to adequately calculate and estimate the uncertainty involved. So that is, we don't know the number of n required for the bootstrap iterations. Due to these limitations, this pipeline cannot be used in a clinical setting. To overcome this problem, we introduce a progressive visual analytic approach in our pipeline. So instead of waiting for the whole ensemble to be ready for fiber tracking, we modified our pipeline such that we perform the while bootstrapping progressively that generates individual tensor volume and fiber tracking at each iteration. With this pipeline, the user can observe the results with increasing completeness and correctness. User can also start the interpretation of the results without waiting for the computation to end. With this pipeline, we get rid of the pre-processing stage, which was the bottleneck in the workflow, and also we don't need to know the required number of samples n in advance. Rather, a user can stop the simulation when the convergence is achieved, which can be interpreted visually. However, this pipeline is still a bit expensive to be used in an interactive workflow. To circumvent this problem, we have introduced our local bootstrapping approach to optimize the bootstrap computations. As you can see here, in naive approach, we have calculated the tensors for all the voxels in the volume. However, mostly a very small portion of the volume is involved in the fiber tracking stage. In local bootstrapping approach, we only perform the computation where it is necessary. We steer through the fiber tracking step by step and calculate the tensor only where it is needed. We modified the current pipeline to accommodate the local bootstrapping approach. This approach further accelerates the computation and optimizes the pipeline such that it can be used in an interactive workflow. To compare the effectiveness of the local bootstrapping approach, we compared the performance of the pipelines by generating 3 different core fiber bundles, that is CST, AF, and OR. We have compared the performance of our progressive approach with the naive approach. As you can see here, in the progressive approach, very few voxels are used, as we have explained it before. In the graph, it shows that a very few voxels has been used in the calculation as compared to the naive approach for all of these 3 bundles. Due to this, we achieved a huge speed up in the computation, as can be seen here on the right graph. Till now, we managed to model the uncertainties and generate the fiber tracks progressively. This video shows the possible variation of the single fiber tract. As you can see here, the samples keep on adding progressively at each iteration. This represents all the possible variation of the single fiber tract. However, it is still very difficult to comprehend the results and extract the relevant uncertainty information from this visualization. Once we model the uncertainty, the next stage is the visualization to provide the uncertainty information effectively and more efficiently. To visualize the whole ensemble of the fiber variations, the most straightforward approach is the spaghetti plot, as we have seen in the video, and it can also be seen here in the picture. It does show the possible variations in the ensemble. However, there is no relevant uncertainty information, and it involves a lot of cluttering. For that, we divided the visualization stage into two parts, aggregation and rendering. There has been several methods presented in the literature for aggregating and visualizing the fiber ensembles. Few of them are listed here. Our approach is very close to the one introduced by Preim. Here is a workflow taken from Prechison's approach. They computed the distance of each fiber with all the others and summed the distances for each fiber and then assigned a distance score for each individual fiber. The fiber samples with the least distance score is considered as the representative fiber, which is the most central fiber in an ensemble. This approach provides a relevant information. However, the main bottleneck of this approach is that it cannot be used in a progressive setting, as it needs the whole ensemble to be available. We modified this workflow such that it works in a progressive environment. Since the fibers are generating progressively, at each iteration a new sample is added. We recompute the distances at each iteration and update the distance score table. We redetermine the representative fiber and update the visualization. To further optimize the computation, we ordered the distance score table such that the fiber with the minimum score, that is the representative fiber, is always on the top. We compute the accumulated distance starting from the top of the table so that we update the visualization first while keeping the other computations in the background. Lower distance scores represents the fiber that are closest to the representative fibers, and higher score indicates the samples that are further away from the rest, and that can be interpreted as having higher uncertainty. Further, to avoid the unnecessary computations, if the distance score of the newly generated fiber sample with the other existing sample is smaller than the predefined threshold, we assume that the fiber sample are similar enough and not need higher precision in the calculation. This further optimizes the computations. Till now, we managed to aggregate the generated samples and assign the distance scores, which provide the uncertainty information on the ensemble. So far, we haven't visualizing anything. The next stage is the rendering of this uncertainty information, which we have calculated in the previous stages. These are the basic elements which we represent in our visualization. First, the representative fiber, which is the most central fiber in an ensemble, is rendered with a red tube. The remaining fiber samples are rendered with the orange polylines. We also provide an interactive histogram to represent the distribution of the distance scores on the fiber ensemble. The left part of the histogram represents the fiber that have lower distance scores and are closer to the representative fiber. The right part of the histogram represents the fibers which are further away from the representative fibers. We also provide a way for a user to interact with the histogram and select intervals to comprehend the distribution of the distance score in the fiber ensemble. As can be seen here, the sample belongs to the selected interval are represented with the blue lines. This helps user to understand the underlying uncertainty present in an ensemble. Here is a demo of our progressive visualization. The visualization and histogram are updated progressively, as can be seen here in the video. The histogram represents the distance score distribution. A user can also interact with the histogram during the computation to understand the distribution of the distance scores. As can be seen here, after some time there are no major changes in the histogram and the shape of the ensemble. At this point, the simulation is set to be converged and the simulation can be stopped. We generate several test cases with our clinical collaborators to prove the clinical relevance of our work and understand the effect of uncertainty in the clinical case. This is one of them. The figure on the left shows the result generated from the algorithm used in a clinical setting. In the absence of the uncertainty visualization, surgeons used fixed safety margins to safely secure the critical brain structure, as can be seen here the blue outline. The figure on the right shows the results with uncertainty visualization generated with our progressive pipeline. As can be seen here, the fixed safety margin is not enough to accommodate the present uncertainty, which can be modeled with our pipeline. The visualization of the histogram and also the representative fiber provides a better understanding of the uncertainty distribution present in the results. In our work, we start with the clinical tractography pipeline and introduced PVA approach for uncertainty modeling and aggregation. We also provide a solution for the effective and efficient visualization and exploration of the uncertainty present in the result. Our approach provides a way for a user to reduce the clinical bottlenecks, and it's proven to be a first step towards clinical integration of the uncertainty visualization. As a future work, we would like to accommodate other sources of uncertainty which are coming from the other stages of the pipeline. And also we would like to explore the effective visual representation and other visualization approaches for uncertainty visualization. Thank you for your attention.
Okay, thank you, Faizan, for this great talk and very interesting topic. And let's start with the Q&A session. So we are having the first question from Christina Gilman. How do you avoid visual clutter when more and more paths are computed?
Okay. Hi, everyone. Very interesting question. Thank you for the question. I think I haven't mentioned in the presentation, what we used for the rendering is a multi-layered approach. So since we have three kinds of visualization, we calculated the most central fiber that we called a representative fiber and the other fiber samples. And to avoid cluttering, what we did, we just render over on the top of each other so that the central fiber is always rendered on the top, and then the remaining remaining fiber samples. And also the interval which I have shown in the video, it is also rendered on the top. So to avoid cluttering, we use multi-layered rendering so that every aspect is visually clear.
Okay, great. Thank you very much. We are having a second question from Nuska Smith. At times, clinicians are a little hesitant about uncertainty visualization. Could you say a bit more about their response?
Wow, that is what I've been doing after finishing the pipeline and finishing the work. Thank you so much for the question, Nuska. And I have been in discussion with one of our main collaborators. He's a surgeon, so they understand the importance of the uncertainty in tractography. But after having few discussions, they are quite skeptical of including this uncertainty visualization in their clinical workflow for now. So that's what I have been trying to do, to reduce the bottlenecks and then make them more aware of the uncertainty visualization and how important uncertainty is in their results, because since uncertainty adds more complications in the visualization, so they are for now they're a bit skeptical to add this thing. But we are still trying to generate more test cases and prove more clinical feasibility, so that later on at some point I hope it will be used in a clinical setting.
Okay, thank you very much. The questions are piling up here, but we are having quite some time for that, so it's good. And so let's go to the next one from Lars Linsen. The approach is very local, considering a single voxel for seeding. How can complete bundles handled? Also, how is seeding supported?
Let me understand the question. I don't know if I understand it. So you are questioning about the seeding or the local approach, because the seeding has been done as similar to the clinical setting right now. So they are just using the seed, a brush approach to select the seeding region. And so which we have created with our collaborators. And for the local approach, I think these are two different things, one of the seeding and then the local approach. For the local approach, we are just going voxel by voxel in the fiber tracking. So first we are done with the seeding, where we know the regions where we have to start the fiber tracks. And then once the seeding region has been defined, then we start the fiber tracks from each point. and then we go voxel by voxel along the fiber tracks.
Okay, thank you. Yes.
I don't know. I am clear
We
or
will
not.
see. Yeah, we will see. Maybe I will ask Lars on Discord, then you can maybe discuss afterwards.
Yeah.
It was not the exact thing he was thinking about within his question.
Yeah,
You
sure.
can continue over there.
Yeah, sure.
Because we are having another question from Helwighauser.
Yeah.
Any chance to make a study where uncertainty would be measured with respect to a ground truth from pathology? Would be interesting to see how close this would match the here presented results.
Yeah, thank you so much for the question. Very nice question. And this is the problem of the tractography, because we don't know the ground truth. And then this is a problem which we have been facing, I think, and we are in discussion with our collaborators and with other radiologists, since we don't know the ground truth, the real data set to actually compare how effective the uncertainty visualization is. And that is the reason, since we don't have the ground truth, that is why uncertainty visualization plays a role. We don't know what actually the result will be. So that's why we are just visualizing the uncertainty and trying to provide more information about the aggregation, so that somehow the radiologists might be aware, they understand how relevant the uncertainty is. But I think in response to the Helwig, if we know the ground truth somehow, like I don't know if there's any open source data which we can use. But if we have anything like that, then we can sure proceed with the study and use a study or something. And it would be a very nice study if we can find any ground truth data.
Definitely.
Yeah.
Thank you very much. Actually, I'll just come back to Lars's question, because he commented on Discord that the question is how larger bundles are handled.
Okay.
That was the topic.
Yeah. Okay. So larger bundles. I think we are optimizing the larger bundles. I haven't mentioned in the presentation right now, but in the paper, I would refer to the paper. But in response to the question, which we are doing after tracking the one fiber, we are actually storing that fiber. So when we are doing the bundle simulation, the fibers are actually very close to each other. So in the bundle, so we are actually reusing the voxels which we actually calculated for the first bundle. So for the neighboring bundles, we can reuse the already calculated tensors. So we don't have to recalculate for the bundles. And yes, that's a very interesting and very nice question, since we were just doing the recomputation and it was not optimized. So to optimize this recomputation, we actually use this approach. So we store and we recalculate for the neighboring bundles, and because of this, I think there's no limitation with how large the bundle would be. But yeah, I don't know what would be the limitation, but I'm sure that we have tried few big bundles and then small bundles, and for now it works.
Okay, thank you. I see that Lars had still some questions, comments on this, so maybe it would be great if you can continue together on Discord afterwards.
Yeah, sure.
And let's have a last question, because we still have time for that, and it's from Thomas Schultz. Do you think it is possible to separate the effects of acquisition uncertainty and fiber spread?
Okay, so let me understand the question. I'm just repeating. So
is it possible, yes, separate the effects of acquisition uncertainty and fiber spread?
Okay, so the fiber spread, one way of the fiber spread is not because of the uncertainty, is maybe the one reason the fiber spread it is because of the bundle looks like that. And to add further spread, it's like fiber, uncertainty, because the uncertainty fiber can be spreaded more. So to possibly separate the effect of the uncertainty for now, what I understand is to actually separate the spread caused by the uncertainty. I think that is the actual question. For now, we are not differentiating between each of the bundle actually there and the bundle and the spread caused by the uncertainty. But we can use different rendering techniques to visualize these two things separately, to only visualize the uncertainty and to visualize the fiber actually present there.
Okay.
Yeah. So
Great.
that is
Thanks a lot. I think this really evoked a lot of discussion and comments and questions. Thanks a lot for all of these. And also for your great answers. And I think there will be some coming again on Discord. So if you can just follow the channel there, that will be great. So Faizan, thanks a lot once again for the great talk and also the great discussion afterwards.
Thank you. Thank you.
Thank you. Well, and now let's jump to the second presentation of today's session, and this will be given by Gabriel Mistelbauer, and the topic is implicit modeling of patient-specific aortic dissections, with elliptic Fourier descriptors. So let's watch the video together, and then we will follow the Q&A session again. Enjoy.
Welcome to this talk. My name is Gabriel Mistelbauer, and I'm with Otto von Guericke University Magdeburg. I'm happy to present our work on implicit modeling of patient-specific aortic dissections with elliptic Fourier descriptors. Before we talk about aortic dissections, let us describe the anatomy of a healthy blood vessel with a single blood flow channel that is referred to as true lumen. If blood enters the medial layer of the aortic vessel wall through the primary intimal tear, the single flow channel, true lumen, is divided into two channels, a true lumen and a false lumen. This leads to a dissected aorta. The cross-section of an aortic dissection could look like this. On the right, we see a computed tomography angiography dataset that shows the true lumen mask in red and the false lumen mask in blue. Our goals are to model smooth surface meshes of the true and false lumina, including the outer vessel wall. Such meshes would allow us to perform morphometric analysis and blood flow simulations. We might also be able to capture and identify prognostically relevant aortic features. The requirements for modeling aortic dissections include different anatomy of true and false lumen, separated by a thin elastic membrane, called the dissection flap. There may also be multiple communications between the two flow channels, but at least one primary intimal tear that represents the onset of a dissection. The workflow of our approach consists of vessel tree extraction, contour extraction, and rendering. Let us first look at the vessel tree extraction. It consists of 4 steps: segmentation, centerline extraction, vessel tree assembly, and MPR volume creation. Starting with the segmentation, we have a computed tomography angiography dataset as input, and obtain a true lumen segmentation mask as shown in red and a false lumen segmentation mask as shown in blue. We then extract the center lines of the true and false lumen segmentation masks as shown in green. If we take a closer look at this location, we have a true and a false lumen. If we use the center line of the combined true and false lumen segmentation for the branches, we obtain the result as shown on the left side. It is important to note that the branches are not properly connected to their parent lumen branch points. Correctly, a false lumen branch should also be connected to the false lumen of its parent branch. Same for the true lumen. To achieve the desired result, we need to calculate the center line of the true and false lumen separately. It is now apparent that the true lumen branch is properly connected to the true lumen of its parent branch. Same for the false lumen branch. The procedure for correctly assembling a vessel tree for aortic dissections is as follows. Calculate the center lines of the entire combined true and false lumens redesegmentation mask and convert it to a graph representation. Keep only branches containing a dissection and remove all others. Then, calculate the center lines of the true lumen segmentation and keep branches that consist only of true lumen. This step is then repeated for the false lumen. Finally, we assemble all branches into the vessel tree. This will ensure that each branch is properly connected to the lumen of its parent branch. Subsequently, the imaging data is resampled along each branch at equidistant intervals, for example, along the aorta. In this way, a straightened volume is generated for each branch in the so-called multiplanar reformation space. Once we have extracted the vessel tree, we extract the cross-sectional contours. This is done in 4 steps: the contour extraction itself, the conversion to a chain code, the computation of elliptic Fourier descriptors, and the reconstruction of the contours for a given number of harmonic coefficients. Let us start with the contour extraction. For each cross-section or axial slice in MPR space, we trace the contour of the true lumen and false lumen. For a true lumen, as shown on the left, we would get the corresponding contour as depicted on the right. The contour tracer categorizes contour points into straight line, inner corner, outer corner, or inner outer corner. We then convert the contour to a Freeman chain code, either 4 connected or 8 connected, by discarding inner corner points. The difference between them is only minimal, and we will use an 8 connected Freeman chain code from now on. The chain code of a contour represents a one-dimensional periodic signal. Therefore, we can calculate the Fourier coefficients. We pre-compute them for 20 harmonics for each lumen separately in MPR space. The true lumen and false lumen contours in the presented image are reconstructed with a single harmonic. This results in an ellipse for each lumen. As shown, we successively add more high-frequency shape information by increasing the number of harmonics. This is one of the motivations for using elliptic Fourier descriptors to represent cross-sections of vascular structures, particularly aortic dissections. Conventional approaches use circles, ellipses, or splines and do not provide means to control the details of a contour. With a higher number of harmonics, the reconstructed contour follows the pixels of the underlying imaging data, which results in overfitting. A good choice is between 6 to 10 harmonics. Whenever the user changes the desired number of harmonics, we reconstruct the contour of each lumen for each vessel branch. We also calculate the outer vessel wall as the convex hull of the dilated contour points of each lumen. The size of the circular structuring element used for the dilation defines the wall thickness. The user can specify a separate wall thickness for the true and false lumen. In the current image, both lumina have the same wall thickness, whereas in this case, the wall of the true lumen is thicker. This reflects a true dissection, as the false lumen lies within the medial layer of the aortic wall, and therefore its outer wall is already thinner. Once the contours have been extracted and reconstructed, the vessel tree can be rendered. This is done in 4 steps. First, we calculate local distance volumes for each vessel branch. Then, we merge them into a global distance volume, place lumen communications, and finally extract the lumen surface. For the local distance volumes, we compute the signed distance field of each reconstructed contour in MPR space, again separately for each vessel branch and lumen. This leads to many local distance volumes. For the true lumen in the current image, we compute a signed distance field with a negative distance outside the shape and a positive distance inside. Subsequently, all local distance volumes are combined into a global distance volume using the smooth maximum function. The left image shows a section of the global distance volume with a true lumen and a false lumen. The distance is 0 outside the lumina and positive inside, with 0.5 being the ISO value for the surfaces shown on the right side. Before we extract the surfaces, we can optionally place lumen communications, also called fenestrations. For example, we could model the primary intimal tear by placing a spherical communication in the true lumen, which then results in a connection between the true and false lumen surfaces. Finally, we can extract the surfaces of both lumina and the outer vessel wall. This is done with the help of margin cubes. Here we can see the surfaces of the true and false lumen reconstructed with one harmonic. Since the cross-sections are represented by ellipses that intersect each other, the surfaces merge. If the number of harmonics is increased to 3, the surfaces of the true and false lumen are well separated. With 10 harmonics, more surface details become visible. But with 20 harmonics, we add too much high-frequency shape information. This concludes our workflow. In the following, we present several results. We created a phantom dataset to demonstrate our approach on common true lumen and false lumen anatomies. At the top, we start with a small eccentric false lumen that twists around the true lumen and increases in cross-sectional area, until only a small portion of the true lumen remains. Then, the true lumen increases and the false lumen decreases. This should demonstrate a false lumen that merges back into the true lumen. As shown, our approach is able to correctly model the common anatomies of aortic dissections. The second part of the phantom dataset should demonstrate the generalizability of our approach to vascular pathologies other than dissections, for example, vascular stenosis. First, we start with a small eccentric calcification shown in blue. Then we have a large concentric calcification, a large eccentric calcification, and finally a large eccentric soft plug. The concentric calcification also resembles a circumferential dissection, in which the true lumen is completely enclosed by the false lumen. This is a limitation of our approach, and the true lumen surface is not captured. Now we describe a specific case, patient 1. This case presents a Stanford type B aortic dissection extending from the descending thoracic aorta to the abdominal aorta. The current image shows a 2 mm true lumen wall thickness and a 1 mm wall thickness for the false lumen. We use 10 harmonics for the surface reconstruction. If you plot the true lumen and false lumen separately, you can see that the true lumen is quite narrow and the false lumen is quite enlarged. This image shows the branches in the aortic arch from the inside of the aorta. Here we can see how the true lumen and false lumen branches are properly connected to their corresponding lumen in the parent branch. The second case, patient 2, shows another Stanford type B aortic dissection. This time, the dissection starts in the aortic arch and goes far down into the iliac arteries. Again, we can render the true and false lumen separately. Looking more closely at the arch, we see a small dissection in one of the branches. Since the dissection extends across the iliac bifurcation, the luminal surfaces should also blend across this branch. This image shows a section through the bifurcation and demonstrates that the true and false lumen surfaces are not merging but extend smoothly across the branch. If we reduce the number of harmonics and contour points, we can create an abstraction of the dissected aorta. For this abstraction, we use 1 harmonic and 4 contour points. For the right image, we reduce the number of points to 3. The abstractions depict well how the true lumen and false lumen twist around each other. We also conducted a performance analysis of our approach. The construction of the vessel tree takes the most time, as it is a semi-automatic process that requires some manual work. The MPR volume resampling is quite fast. Contour extraction and elliptic Fourier coefficient precomputation for 20 harmonics takes only about 22 milliseconds. The reconstruction of the contours takes about 16 milliseconds. All rendering steps are performed on the GPU using OpenGL compute shaders. The distance field calculation is generally very fast. The most time-consuming process is extracting the surfaces using margin cubes. This usually takes about 1 to 2.5 seconds. We conducted a user study consisting of 8 participants to obtain feedback from experts. 6 participants had a clinical background, while 2 participants had a technical background. We gave them a questionnaire consisting of 6 questions. For the answers, we used a 5 or 7-point Likert scale. Before completing the questionnaire, we explained our approach to the participants and showed them a demonstration video. Concerning how do you rate the visualization for aortic dissections compared to clinical, traditional, or current volume rendering, participants found our approach somewhat to much better. The participants found the ability to display true lumen, false lumen, and outer vessel wall separately useful. The limitation that circumferential dissections cannot be currently modeled was found slightly acceptable. For quantifying aortic diameters or dimensions, computational fluid dynamic computations, 3D printing of models, statistical analysis and modeling, surgery planning and visualizing changes over time, participants found our approach suitable. In terms of importance for clinical application, participants found our approach moderately to very important. In terms of importance for research and future development, participants found our approach also moderately to very important. Let us recapitulate the requirements for modeling aortic dissection to conclude my presentation. Concerning a diverse true and false lumen anatomy, we showed how to model arbitrarily shaped vascular cross-sections, which are separated by a thin elastic membrane, the dissection flap. We also showed how to establish communications between the lumina. As we fulfill these requirements, we reached the goal of representing smooth surfaces. We also showed how to control the degree of smoothness and abstraction. Based on our approach to model aortic dissections, we can now address the remaining objectives as next steps. Among them are the morphometric analysis of the cross-sectional shapes, blood flow simulations, and the acquisition and identification of prognostically relevant aortic features. Thank you for watching.
Gabriel, thanks a lot for this great talk. And the questions are appearing one after another. So let's start with the first one, which is from Christina Gilman. Especially for vessels, it can be really hard to extract them due to a variety of image artifacts. How do you handle them?
Yeah, so thanks for the question and hello. So currently it's quite a semi-automatic process. So some vessels like the aorta are segmented automatically with a machine learning approach. And the other smaller vessels are automatically tracked and then manually refined. So if there would be artifacts currently, then we would correct them manually. Of course, there is always space for improvement there to have a better segmentation algorithm.
Okay, thank you very much. Then we are having a couple of questions from Marco Agus, and let's start with the first one. How many cross sections do you need to obtain adequate results?
Yeah, that's a very good question. So the results presented, we resampled at 3 mm intervals along the center lines, but in general, if it's too sparse, then there is a lot of interpolation going on, and you also have to increase some other internal parameters, and you will get some smoothing artifacts maybe between the cross sections. If it's too dense, then you might have too many high frequency details. So there should be like a trade-off, I would say.
Mhm.
So quite a lot actually. 3 millimeters, if it's like 30 centimeter in length, then there are a lot of cross sections.
Okay. And between two cross sections, do you have some interpolation schemes for contour coefficients, or?
Not for the coefficients, but of course this can be done. That's actually a very good idea, but the interpolation is then done in the blending along the cross section.
Mhm.
So there is a kind of
Mhm.
blending between these cross sections.
Mhm. And there's a suggestion for like some future extension to some other domain. So I think that the scheme could be also applied to other tubular structures like neural processes. Did you plan to do that?
That's actually a good idea.
Mhm.
This was also one of the motivations to have kind of a would say very general scheme of how to represent cross sections and arbitrarily shaped cross sections, which are not only convex. So even sometimes in dissected cases, there could be two false lumina. So you have like 3 flow channels. So I would say, yes, that's possible. And I would be happy to do that.
Great. So let's do that.
Yes.
There is another question from Björn Samuel. Follow up on Marco's one. How realistic is it to apply your approach to more complex lumen structures such as mitochondria in the near future?
I think this also goes hand in hand what I said before with this question. So I think it's possible and realistically to be applied there too. Yes.
So you have some stuff to do.
Yes.
And there is another short question from Helvig Hauser. How many of the study participants are also co-authors of the paper?
2.
Thank you.
Welcome.
So we are running out of time slightly and also out of questions right now, but I'm sure that there will be some upcoming on Discord channel. So if you would be so nice to
Yes.
go check the channel over there as well. And there are many congratulations for great work and talk everywhere on YouTube, Discord. So you can just look at that and enjoy. Thank you, Gabriel, once again for a great talk and the session. Thanks.
Bye.
And let's jump to another interesting talk, which will be about visualizing carotid blood flow simulations for stroke prevention. And the talk will be given by Pepe Eulzer. So enjoy the talk and the video.
Hi, I'm Pepe Eulzer. I'm with the University of Jena in Germany, and I will talk about simulations of carotid blood flow and how they can be visually analyzed to aid in stroke prevention diagnostics. So stroke is one of the leading causes of death worldwide. Even non-fatal strokes generally lead to permanent neurological disabilities, so stroke prevention is a highly prevalent topic. Most strokes, close to 90%, are due to reduced blood flow to the brain. This is typically caused by what is called vessel stenosis. This describes a localized narrowing or constriction of the vessel. Such stenosis can develop gradually through atherosclerosis, which can be life-threatening if it occurs in one of the 4 vessels that deliver oxygen to the brain. And most frequently this happens in the carotids. These are the 2 large arteries that run along your throat, where you would also feel your pulse. And this is why stroke patients or patients with a higher risk of stroke they often need to undergo carotid screening, where physicians determine whether such vessel stenosis are present and if they need to be treated. If it's not too late, stenosis can be removed surgically, which is also often done as a prevention procedure. However, vessel surgery comes with its own risks, so careful consideration must be made regarding the necessity of these types of interventions. And therefore it is crucial to understand 2 aspects. One is vessel morphology, the shape and form of the vessel, and the other are the hemodynamics. These are the properties of the blood flow inside the vessel. Standard prevention and diagnostics rely on two methods. The morphology of the carotids is analyzed with CTA. This is CT with a contrast agent that highlights the vessels. This gives you an understanding of what the stenosis looks like. And the hemodynamics, on the other hand, are analyzed with Doppler sonography, which provides information on the speed, flow direction, volume of blood flow. And so the obvious problem here is that you need to mentally combine this information to get the full picture. Now, instead of performing these two separate assessments, we investigated how blood flow simulations generated with computational fluid dynamics could be used to supplement the CTA data with hemodynamic information, and this would allow a combined evaluation of all properties. Our approach follows this typical pipeline. We obtained 13 CTA datasets of different patients, from which we segmented the carotid arteries on both sides. And on this geometry, we perform a CFD simulation of the blood flow, where we use a standard velocity profile at the inlet that models a typical heart cycle. And this gives us a set of discrete points in time where we know the flow properties of the volumetric grid that is framed by the vessel geometry. And we also compute the vessel center line, which we will use later. Okay, so up to this point, this is a typical approach that is often used in CFD research, also in visualization research around blood flow, so we've probably all seen this. Now, the real problem is that computing the flow this way can generate a lot of data, and clinicians struggle to get any insights from that data. So we talked to a neurologist and a radiologist who routinely treat stroke patients, and we analyzed the types of tasks that they are confronted with, which allows us to abstract these tasks and represent the data accordingly. So the typical tasks condense to the following. First, stenosis need to be identified, and this step shouldn't be overlooked because more often than not, patients have multiple stenosis, and all of these need consideration. And essentially, this boils down to getting an overview of the parameter space and detecting relevant points. And second, morphological features are analyzed, like the vessel diameter and the length of a stenosis. And similarly, hemodynamic features are analyzed, where physicians are interested mainly in flow velocity that will increase inside a stenosis. And they also look for turbulence that can occur after a stenosis. So the abstract task that is implied here is to probe selected spatiotemporal data points. So these are the primary tasks, but we also found that some processes occur in the background while these assessments are made, and these are similarly important. So for one, the left and the right side carotids of a patient are often compared, where differences in shape and diameter can indicate pathological processes. And also the location of a stenosis determines which treatment options exist. So for instance, you need to know if the constricted part of the vessel is inside of the skull or outside. And on a CT scan, this location is of course obvious, but remember we created these vessel models which don't tell us anything about the surrounding context. So yeah, physicians rely on this context, which is why we do need to keep track of it. Now the question is how to incorporate this knowledge about the tasks into the result visualization. And you might know that there is a corpus of research on similar topics such as flow and aneurysms, but as far as we know, we are the first to investigate flow visualization regarding stenosis. But still, instead of reinventing the wheel, we put down the basic assumption that many of these generalizable methods developed in FlowVis are applicable here as well, and we selected what has proven to be useful. So the key methods evolve around overview, temporal analysis, probing, and contextualization. Overviews should guide towards points of interest. Often wall-related parameters are, for instance, shown with a color map, and illustrations of the flow field can be displayed through integral lines, glyphs, or particles. And tree-like structures can be dimensionally reduced to maps, graphs. This is also a frequently used technique. And temporal analysis can be facilitated through juxtapositions, animations, or integrated displays of multiple time steps. And for probing, a variety of methods were developed. The most promising for longer stretches of vessels, like we have them here, are probably so-called slice widgets that can display cross-sections of the flow field and contour the vessel walls. And then contextualization is sometimes split into visualization of the near and far context, meaning sometimes close structures of interest and like the vessel wall, and sometimes far structures like the surrounding tissue or bones. In our case, we need both, but I'll get to that soon. So we developed this framework that integrates the results from our pipeline to help physicians explore the flow fields and make the data actually useful to medical practice. We combine 4 linked views. First, a 3D view of the model, then a graph that shows the blood flow rate over time. And below that, we show a simplified view or map of the vessels. And last but not least, a probe view where you can see cross-sections of the computed fields. For the overview task, we display the vessel geometry in the 3D view, either as a surface, or you can also switch to a streamlined depiction. And we then map a parameter, in this case, the velocity magnitude, with a color map. And in theory, the user can view any scalar field like this, but we focus on flow velocity for now, as it is similar to the information that you would get from sonography. And we first wanted to test this with data types that the physicians already know. When a stenosis develops, it first results in a higher flow rate at that location, as the circulatory system compensates for the vessel constriction. And then when a stenosis gets more severe, what you'll see is this turbulent flow where the vessel gets wider again. So turbulence occurs when the bloodstream slows down abruptly. And these two factors are nicely visible in the streamlined depiction. However, it is hard to read any exact values from here, and the 3D geometry is also sometimes self-occluding and can be difficult to navigate. Therefore, we provide this second overview depiction that shows a map of the vessel tree. This is a 2D representation which is automatically generated from the vessel center line, and we encode the diameter as the line width, so thin regions can be quickly identified. And this map then doubles as a tool for spatial navigation, where you can set at which point you take the probe of the vessel cross-section. And you can also drag the probe over the map, and it will change its orientation to follow the vessel geometry. So the accurate cross-section is displayed, and the physician will get a good impression of the actual diameter at this point. This means setting a plane cut along the flow volume can be done extremely fast. Minimal interaction is required to place the probe, and no interaction at all is required to orient it. We create the vessel map with several aspects in mind. So first, we identify all the different branches that may be present in a model, and then we take the longest branch and lay it out straight. This is the internal carotid, the one that supplies the brain. So it is the most important segment, and the other segments are then also added at a fixed angle to give this representation a visual coherence. And what's basically the crucial parameter for the overview task is the vessel diameter. So we map the diameter to the width of the map lines, and we use this nonlinear scaling that highlights possible stenosis by emphasizing thin parts of the vessel, which can then be examined more closely using the probes. We also preserve the geodesic length of the center line, which makes this map really useful to quantify a stenosis. For example, here you can measure that this stenosis affects about 20 millimeters of the vessel, where we also show the computed diameter below the probe view here, and you can use this millimeter grid to get a size estimation of the cross-section. So remember that one of the tasks we identified was comparing the left and right carotid of the patient. So to facilitate this, we aligned both vessels in the map view. And to make them comparable, we register them at the bifurcation where the external and internal carotid splits. So this is a clearly defined landmark that physicians are accustomed to. So when you find a stenosis, you can quickly set the second probe to show you the cross-section at the other side. And here you can see how small the diameter becomes in comparison to the healthy side. The data is also temporarily resolved, and we included the small graph to give a representation of the underlying cardiac cycle. It shows how much blood volume is passing through the left and right carotid. Usually what is interesting is the time point of highest flow, so it's called the systolic peak, but the user can also drag the slider and look at different points in time, for example, to see if a turbulence is persistent over multiple heartbeats. As I mentioned before, this 3D depiction of the segmented models may hide some context information that you could get from the original CTA data, which would go against what we're trying to achieve here, which is that you can analyze all the information, morphology, hemodynamics at once. So to make this more viable, we built the framework such that it can integrate the original CTA data in addition to the simulation results. The 3D view then shows a combined volume rendering of the segmented models and the volume image. To keep the controls for the volume rendering simple, we integrated just two sliders. So one controls the opacity and the other one controls the visible values. So the user can visualize dense regions like bones or the vessels highlighted by the contrast agent or even soft tissue. And most of the time this depiction is relevant to localize a potential stenosis, for example, if you want to know if it's inside the skull or not. But you can also derive some other context information, for instance, if there are structures that would prevent surgical access to the stenosis. The CTA data can also be used to extend the probe view. We sample the volume with the cutting plane, so this shows a view of the original data that also follows the vessel, so the user can examine the anatomical context around the cross-section. The user can also define if an overlay of the flow data is required, and on modern graphics hardware we can sample the volume fast enough that the probe remains draggable, which means a physician can smoothly examine the carotid following the vessel direction. And this gives an undistorted view on the actual diameter of the vessel, even if it is weirdly shaped or bent. The user can decide if the overlaid blood flow information is required. We have found this type of interaction is highly useful when plaque on the vessel wall is examined. So atherosclerotic plaque is the typical reason for a stenosis, and its color, size, and shape can provide a lot of information on pathogenesis and the severity of the stenosis. As we align the cutting plane orientation to the vessel, the plaque can be examined in a consecutive motion that is perpendicular to the ideal vessel cross-section. So this provides an undistorted view on the amount and location of plaque buildup. We evaluated our framework with 7 domain specialists. Primarily, we spoke to 4 physicians who treat stroke patients and perform stroke prevention diagnostics and treatments. And we also conducted reviews with 2 CFD and 1 FlowVis expert, as physicians might not know what's the state of the art with simulation and visualization methods. So we wanted to approach this as the interdisciplinary problem that it is. We performed interviews following a think aloud process where we had the physicians interact with several data sets with different types of stenosis, and we asked them what they could tell us about the data and which information they could gain from the visualizations. So the doctors generally defaulted to a single time step at peak flow and then quickly identified the stenosis on the map and in the 3D view. Then they mainly used the framework to probe the surrounding velocities and the vessel diameter, where they made extensive use of the map and the probe depictions. They also heavily used the contextual CTA slice around the probe, and they liked the overlay of hemodynamic information on top of the CTA. So just from a visualization point of view, we are fairly certain that the experts would find a tool like ours helpful for analyzing the individual stroke risk due to carotid stenosis and to decide if treatment is necessary, and yes, whether surgery would be required and what type would be ideal. The medical experts made this point clear in our discussions and also in the questionnaire they filled out. Still, in some discussions, we were reminded that many clinicians see the validity of simulated flow data as the major barrier to practical adoption of methods like the one presented into clinical workflows. Now, I'd like to conclude this presentation with an outlook on this issue, because what we did was we revisited this discussion with a group of researchers on both sides. So we had CFD researchers who work with blood flow simulations and clinicians who work in stroke care. And we believe, and I would like to highlight this point, that one of the core problems in this research domain is that we have a lack of cross-domain communication that would be necessary to drive development. And what we could observe is that there are advances in the CFD domain, and we're getting closer to being able to realistically model human blood flow, but these advances are rarely brought to the attention of practicing physicians. And there's also the exact reverse problem, where the requirements of physicians, so what's actually needed in acute stroke care and stroke prevention, they are often completely unknown to researchers in the field of CFD. And obviously this bottlenecks clinical integration of computed flow data, even though we know that there are areas where this could provide a real benefit. For example, here we could see how excited physicians were to be able to assess morphology and hemodynamics in a single depiction instead of relying on different diagnostic methods, which they currently need to mentally combine. This is why we see tools like the one I presented more at this interface between flow simulation research and medical practice, as we believe it can demonstrate the usefulness of this kind of data and make a case for large-scale clinical trials, which are ultimately the only way to get a real validation of such approaches. Okay, to wrap this up, just a few key takeaways. We found that concepts from FlowVis research can be transferred to match specific tasks in the domain of stenosis analysis. And I'd also like to highlight the importance of contextualization in medical applications like the one I presented. This is really a core feature of this work, as context information can be used for many tasks like localization, feature exploration, as I showed with the plug example, and even to perform on-the-fly validations of the segmented 3D model. Also in this study, developing the right exploration techniques was similarly important as choosing and adapting fitting visualization methods. So we hope that our approach will help physicians to explore this kind of data more effectively, and that it will foster communication between researchers and practitioners and ultimately promote the practical integration of CFD-generated flow data in stroke prevention.
And we are having Pepe here for the Q&A session. So first of all, thanks a lot for this great talk and work. It's really excellent and beautiful, I have to say. And I'm not the only one. Afterwards, you can check Discord that people also enjoyed this a lot. But before that, let's take some questions. We are having the first one from Christina Gilman. Can you explain more about the segmentation process and if it was performed by the clinician, how the clinician is supposed to perform this in a clinical daily routine?
Yes, so thank you for the question. Yeah, so we used the VMTK to segment the vessels. Most people here probably know what that is. In an ideal world, I would want the segmentation to be close to automatic, and the same goes for the simulation, of course, so that the clinician has nothing to do with that. But in reality, as you're probably aware of, like a lot of tools claim that they can segment vessels automatically, but this is actually easier said than done. And for example, for the carotids, we often have heavy artifacts that come from metallic teeth fillings, and these are exactly at the same height where the stenosis also occur. So this is really bad for automatic segmentation. Also, stenosis are often not round. They are, this is often an assumption for many tools that segment vessels. And so that means that in our case, for our data sets, in all cases, we had to make manual corrections. So this is still a bottleneck. And the methods are getting better, but I believe that currently they're not quite there yet for clinical application.
Okay. Thank you very much. And we are having another question from Bernhard Preim. First, he congratulates for the really nice work. And then he's asking how the blood flow actually may affect the surgical strategy in case of asymptomatic stenosis. Or is it more for research-oriented understanding of flow phenomena?
Yes. Thank you for the question. So for anyone who doesn't know, asymptomatic stenosis is that this means we see a stenosis, but there are no symptoms. So you could also say the stenosis is stable. The brain can also be, for example, supplied by the other side carotid in some patients. So this is the hard case where you need to decide if surgery is necessary or not. So our idea is that you can use the tool to get this kind of overall depiction. So you can assess, is the plaque buildup, is it new or old? Are other stenosis present? Is the turbulence strong or weak? And then you can use this combined information. Mm-hmm. But to actually validate this, as I also said in the talk, we would need large-scale clinical trials, which are currently rare in the case of CFD or applied CFD. So currently we use the tool to kind of bridge the communication between CFD and medical researchers. So we want them to like detect patterns and see how the morphology affects flow and vice versa.
Okay, thank you. Thanks a lot. Actually, we are having one idea for future work from Bernhard here as well. So to conclude this part, stroke is often caused by ruptured plaques in the coronaries. Thus, integrating these vessels in the analysis and estimating the plaque rupture risk may be useful. So it could be interesting direction.
Yes.
For improvement.
Yeah, I agree with that. So this is also what I push for currently. I want the whole picture. I want more vessels segmented and simulated so that we can see like the smaller branches in the head, which are actually interesting for stroke care, because this is where we often get where the ruptured plaque travels up and then clogs a vessel in the head, and then only a certain part of the brain is affected. And this is important to see where this is and how it affects the vasculature.
Okay, perfect. Thanks a lot for your answers, your comments, and good luck with your future work. And we are looking forward to next papers at next conferences. And so let's conclude this talk and jump to another one. Thank you very much.
Thank you.
So the session is almost over, but wait for the last talk of this session, which will be also exciting as the previous ones. And this one will be about visual identification and correction of neural circuit errors. The tool is called EuroVis, and the talk will be given by Felix Gonda. So enjoy the talk.
My name is Felix Gonda. I'm a graduate student at Harvard University studying computer science. Today, I'm going to talk about our paper EuroVis, Visual Identification and Correction of Neural Circuit Errors. Before I start, I would like to thank my collaborators who have all contributed to this work. So this work is inspired by connectome reconstruction. A connectome is a digital wiring diagram of the individual neurons in a brain. Why we're studying this is because we want to advance medicine by enabling scientists to understand the brain in health and disease, and we want to advance computing by enabling computer scientists to build better algorithms and intelligent machines. So the process of creating a wiring diagram involves a workflow. Here I've shown a very simplified version of that workflow that starts with electron microscopy images. These images have undergone alignment transformation, and the first step to reconstruction is to do segmentation. And segmentation involves assigning a label to every pixel according to what neuron it belongs to, and also detecting where the synapses are. Then following this step is a manual proofreading, which is typically performed by an expert neuroscientist who inspect the automation results to see where errors are and fix those errors before the final graph is analyzed by scientists. Proofreading, however, is a very challenging task because typically the proofreaders have to inspect large volume of data sets that are reconstructed automatically. For example, here you see a dense reconstruction of neurons and synapses. And proofreading typically involves two tasks, synapse proofreading and neuron proofreading. So synapse proofreading, for example, here, you see the blue structure here. That's a synapse location that's connecting this yellow neuron and this pink neuron. So proofreaders have to go through the entire data set, find where these locations are, and validate and make sure that they're correct. If it's not correct, then they fix them. Now, this is a very problematic task because the density of synapse is very high, usually is in the millions, and also the synapse locations are inefficiently organized, which leads to redundant inspection of data locations. For neuron proofreading, typically there's a lot of errors. So, for example, here, this is a split error where the automation thinks that this should be two neurons, but actually this should be one neuron. So in order to find this kind of errors, the proofreader need to go through the entire data sets, find these errors and fix them. And this is problematic because the density of neurons is very high, as you can see here in the volume. And then there's also the reconstruction of neurons a lot of time is partial, meaning that a single neuron could span multiple volumes before you capture the entire structure. The other problem is the workflow issues. For example, to do a proofreading task, you have to go through a 3D inspection tool to see the structures in 3D, and then go to a 2D tool to fix it at the pixel level, and then go to a spreadsheet to document the structures. This becomes tedious, especially when you scale to large data sets. This problem has been looked at by other researchers. For example, here you see a set of tools proposed by previous researchers. VAS, for example, is a proofreading tool that's very good at 2D level editing. And then there's the eyewear and Nu2 that provides you, in addition to the 2D, it gives you the 3D and collaborative features. And then you have guided proofreading that detect errors and prompts the users to correct them. So with our EuroVis strategy, our approach, we're trying to take the best of this proofreading functionality and really focus the user on the task of proofreading, which is inspecting locations that are suspicious. And so we're going to do that by doing an automatic error detection that will enable us to focus the users on those locations. And we want to heavily help the user in terms of classifying the neurites so they don't have to document them, and also to focus on connectivity, meaning proofreading of synapses. So we employ a set of strategies. The strategy starts with the automatic reconstruction. As I mentioned earlier, this is densely in terms of the synapses and also the neurons. It's very hard to inspect errors. It's very hard to examine connectivity. So our first strategy is to go to single cell proofreading. What this means is, first we're going to skeletonize all the neurons, and then we're going to limit proofreading to just a single neuron and its immediately connected partners. So, and we limit this to up to 15 partners. Why we're doing this is because in the worst case, you could have a neuron that is connected to every other neuron. But limiting it in this way basically allows you to not only visualize things better, but also to make it easier for proofreading. Then the next thing is we're going to do an automatic classification of neurites. So what that means is basically given a cell like a neuron like this, the branches of this cell means different things based on where the synapses are. So if we know where the presynaptic and the postsynaptic contacts are, then we can classify, for example, here the blue is the presynaptic contacts, then we can classify this structure into an axon. And then where the green synapses are, we can classify those, because those are postsynaptic contacts, we can classify those as dendrites. We also provide manual classification tools where you can select multiple structures and drag and drop them into the right category if you know that they should be axons or they should be dendrites. Okay, then the next thing is we want to optimize the organization of the synapses so that to make it easier for proofreading. To do that, synapses are typically located to neurite structures. So we're going to take synapses within proximity of structures, and we're going to group co-located synapses into clusters. And then those clusters, we're going to sort them so that they're spatially next to each other in the browser, which I'll show you in a second. And within each cluster, we're also going to sort the individual synapses spatially so that they are close to each other. So this results into this sort of graph organization within the browser, so that like all these synapse sets, which are the clusters, they're next to each other here, and also in the 3D space, they are also next to each other. So this is very useful for proofreading, because typically proofreading is done on a structure by structure basis, meaning you want to take one structure, proofread that entire structure, and move on to the next one. But you want to do it sequentially, not just jumping around from random location to another. Okay, then the final thing we want to do is error detection. So error detection here, we're doing it because we want to guide the user to focus on the locations that we think are suspicious. And the way we're doing that is we're detecting a few of the errors automatically. So one of the errors is the invalid branch. So typically when neurons branches, they tend to branch in the same direction like trees. But every now and then, if you have a neurite that branches in the wrong direction, then we need that to be inspected by the user to confirm that this is indeed correct or it's incorrect. So we can detect this automatically by basically taking the direction of the stem and the direction of the branching neurite and using the dot product. If it's negative, then we know that this is suspicious and it needs to be inspected by the user. The second type of error is the broken neurites. So this usually happens if the automation thinks that these should be split into two neurons, right? And in this case, it's not. It's not supposed to be split too. So to find this kind of errors, we're going to check the endpoints of each neurite to see whether there's a structure close by that should be connected, right? And if we find a structure, then we're going to confirm it using this recurrent neural network. So and the way we do this is basically from the endpoint, we're going to apply this network, and then we're going to predict to see if there's any object that should be actually connected to that endpoint. And if that's the case, we're going to flag it because we want the user to correct that mistake. And then finally, the other error is the disconnected neurite, which is basically neurites that terminate within the volume and have no synapses at the endpoint. And these are very easy to detect because you just need to go to the endpoint and then within a certain radius threshold, check whether there's synapses there. And if there's none, then you flag it so the user can inspect it. Then finally, we provide an error inspection tool called Inspector. So the inspector attaches to a neurite and it moves along the skeleton of the neurite so you can inspect it. In this case, here you render the segmentation, the automatic segmentation within the volume, because we don't want to load it. We don't want to load the entire segmentation, but rather only the segmentation within this volume. And then we also allow you to inspect using a 2D plane that's integrated into this inspector that you can move up and down. And then we allow you to also fix errors in the 3D space. For example, to fix this fix the split error, you can just tag the endpoint of the two structures and then click a button to merge them, and that will automatically fix the segmentation. So we conducted a user study using 6 expert users to sort of examine the average completion time for 6 neurons and also the average number of edit operations for 6 neurons. So in terms of comparing the synapse proofreading, we drastically reduce the average amount of time to less than 2 hours. And why that number is drastic is because, as I mentioned earlier, for synapses, we really focus on doing the clustering and also organizing the synapses such that when the user do validation or proofreading, they are proofreading a bulk of synapses in one shot as opposed to jumping from one random location to the next. And then for neurites, we also reduce the number of the average amount of time, because now you're actually zooming into the location that's suspicious as opposed to just inspecting everything in the data set. And then in terms of number of edit operation, here we focus on what the user is actually editing. So previously the user focused a lot of time on doing the bulk of classification operation. But now, because we're doing most of this operation in bulk, it reduces the amount of time that is spent on doing classification. And then in terms of changing the actual segmentation, for synapses, that number remained the same, but for neurites, that number reduces drastically, because in our system, we focus on proofreading connectivity. So if if a segmentation error is not involved in a neural pathway, we don't really care about it in our system. And then finally, we did a subjective feedback in terms of how people felt about our system. So from a confidence point of view, people felt very confident in using our system. The learnability was very high, because people felt that the tools that we provided were a lot more familiar and did not require much training to use them. And then in terms of the strategy we employ for proofreading, the single cell strategy was a lot better in terms of making it easier to inspect errors and also to see how neurons are connected to each other. And then in terms of completeness, this measures whether the tools provided the complete functionality. So in this case, it's equal. And then overall, people felt that our system was much better because we provided a unified interface, and you don't have to switch between different tools. And also the bulk classification, the automatic classification, was so much helpful in terms of reducing the amount of time spent on documenting structures. So we provided a proofreading app that allows you to navigate to different data sets. Once you load the data set, it shows you the individual neurons. So we take pictures of the neurons, and then we show you the status in terms of the progress of proofreading. We also show you who it is assigned to. And when you click on the neuron, it loads the interface. So the interface consists of the browser, which shows you the synapses, the errors, and the neurites. And then in the middle here is the 3D viewer that shows you the segmentation and the skeleton of the neuron. And then there's the editing, the segmentation editor that allows you to paint and change the actual pixels and the segmentation. And then in terms of proofreading synapse locations, here you're looking at the local circuits, and the big green structures are the synapse clusters, and the small ones are the individual synapses. So here you're looking at how the two neurons are connected. And then this is another look at the inspector tool, that when you zoom in, it has this 2D plane that allows you to inspect the segmentation on a plane at the 2D level. And then here we have this view that shows you where the inspector is located relative to other objects in the volume. So this is the entire volume, but then this is just where the inspector is located within that volume. And then in the 2D view, you can look at the structure that you're inspecting, either using the plane, or you can just inspect like the 3D structure, this 3D segmentation itself. Okay. And then here we showed a 2D render of a local circuit inspection, where a presynaptic cell is connected to a postsynaptic cell, and here we show a single synapse and how it's connected at the structural level, so you can know actually which axon is connected to which dendrite. And then here we show a proofreading of targeted, a targeted proofreading showing morphological, showing structures with similar morphological features. So in terms of future work, we think that the next step would be to investigate connectivity patterns. So this would be like motifs, how certain neurons are connected, and this could be indication of maybe some hypotheses that biologists are exploring, and this could help them in investigating those kinds of hypotheses. And then the other thing is looking at high-level exploration tasks, such as like comparing local circuits. So there could be, maybe related to the connectivity patterns, you could have certain neurons that are connected in a certain way, and you want to compare how the circuits are connected, and that could give you maybe further insights. And then finally, you could do classification of components based on a biological function. And currently, a lot of this is done manually, and if we build the tools necessary for doing all this work, then it could actually accelerate the analysis process.
Okay, Felix, thanks a lot for this exciting talk and also for this very important and interesting work. And again, I'm not the only one who is saying that. The same says Marco Agus in his comment and also upcoming question. How sensitive is the system to the accuracy of skeletonization? How do you get them?
Yeah, so the skeletonization system that we use is actually from Princeton University. So it's not our system, but we just use their system to extract the skeletons. Mm-hmm. It works pretty well for our data set, but I think sometimes if the data has a lot of artifacts, you may run into problems. So there may be some more research that needs to be done to improve the tool. But that wasn't, the implementation of the tool was not part of this research.
Okay, perfect, thank you. Another question is from Nuska Smith. Amazing work again. I have another application that could use interactive segmentation proofreading, microvasculature in mice brain. Could your tool be applied directly to other imaging data like this, or are there things specific to your neurosegmentation context? Is your tool available online to try?
Yeah, so yeah, the tool will be available. I am actually working on putting it out on my website. Yeah, so the tool, yes, it can be applied to other data sets. Actually, another work that I'm kind of working on trying to get it to is using it for pathology. So the idea is really just the proofreading of structures is not really just, it's not limited to like neuron structures. You could proofread any data set that can be, that can have very specific structures that a biologist is interested in. Because the problem is that automation is never always 100% accurate. You can get like maybe 95% accurate, but the problem is that 5% that may be the problem. And so you just want to focus on that. And that's where the proofreading comes in. If you can automatically detect those errors, then it sort of like saves you the time of having to look at everything else that is not necessary to. So,
Okay.
so yeah, I will be putting out the tool in the couple of weeks, in the next couple of weeks. Yeah.
Amazing, thank you, Nuska. You can look forward to test your data. That's
Right.
great. Another question is from Björn Samme. Again, impressive work. As you might be working with partly very large data sets, what are the size limitations? What data sets are compatible?
Yeah, so currently the data set that I work with, one of them is from Genelia Farm, which is publicly available. It's from the Drosophila data set. So you can find that online on the web, actually. I also work with local data set because we have like a Center of Brain Science that I collaborate with. They're actually part of this research. And in terms of the limitations, really there are two aspects. There's the offline processing, and that typically there's not a lot of limitations there because typically we split the data into smaller chunks and then recombine the results after processing. But the bigger challenge is really when you are loading data on the visual interface where you're doing interactive processing. And so for that, really the limitation is going to be the number of neurons. In the worst case, you can have a neuron that is connected to every other neuron in the data. But we have that parameter that I talked about earlier that limits it to like up to 15. But you can still, that could still be problematic. But we allow the users to sort of like limit that number. I think like for future research, probably it may not be a good idea to use that parameter, maybe focus on things like motifs, like connectivity patterns that the researcher, more scientists are interested in exploring. So you limit the number of neurons maybe based on those aspects as opposed to just having a hard parameter that the user control. So but that's part of future research that I think should be done.
Great. And there is a follow-up question from Björn related to the web-based solution. He's interested in that. If it is working in the browser, how do you manage to import large data sets there?
Yeah, so the trick is that what we render is actually the center line of the neurons. So that actually saves us a lot because we don't need to load the entire data set. The other thing is that we don't actually load the raw data or the segmentation data onto the interface. Rather, only when you select an error, then we only load like the volume closer to the error location, because that's the section where the proofreader is interested in examining the data. But otherwise, you just only need to visualize the center lines. And I think that's where our saving is really,
Okay, great. Thanks a lot. Thank you very much for everything, for the talk, for the work you are doing, for answering the great questions from our audience, and good luck with your future work. And we are looking forward for the release of the tool.
All right.
Thank you very much, Felix, once again. And basically, that's the end of this session. Wow, this was amazing, right? Did you enjoy it as well? So thanks a lot once again to all the speakers of this session for their great talks and work. Thank you for your questions, for attendance, watching the videos and asking great questions afterwards. I would like to also thank our technicians and our volunteer, because they are doing a great job here at the backstage. And enjoy the rest of the conference. This concludes this session, and hope to see you soon in person. Thank you very much, and bye. Bye, everyone.